Good morning, fellow chemists. We're going to learn how to do limiting reactants problems with BCA charts. So we're going to take what we learned about limiting reactants and we're going to take what we learned about BCA charts and the calculations and put them together. Here's an example of general problem that I made up with some nice round numbers and a chemical equation that we're really familiar with. So if 100.0 grams of aluminum reacts with 150.0 grams of oxygen, how much product will be formed? How much of the reactant in excess is left over? So let's remember about BCA charts. B stands for before, C stands for change, and A stands for after. So before is going to come from the givens. And the givens in this case are 100 grams of aluminum and 150 grams of oxygen. Now, when you see a problem that has two givens of two different reactants, you want to think to yourself limiting reactants. Otherwise, how would you pick out which given to use? So let's remind ourselves again about the tricks that we use. Because in our BCA charts, the amounts that we add always have to be in moles. So when we want to go from grams to moles, we would divide. If we were needing to go from moles to grams, we would multiply by the molar mass. So if you put those little symbols at the top of your assignment, then you can remind yourself so we don't have to do problems each individual step of the problem. So I know that 100 grams of aluminum divided by the molar mass of 26.98 will give me the value in moles. Now, usually you're going to want to leave the word mole out of the BCA chart just because it gets too messy otherwise. And then I've got 150 grams of O2, and the molar mass of O2 is not 16 from oxygen, but 16 times 2 for O2. So I'm going to divide 150 by 32, and I get the starting value of 4.6875 moles. Remember, before the reaction even starts, we have zero products. So the products always get a 0. Now let's remind ourselves what the change column means. These coefficients from the balanced chemical equation are the mole ratios. So the first thing we'll do is bring down the coefficients from the balanced chemical equation. Now let's remind ourselves, a chemical reaction, by definition, is putting chemicals together and turning the reactants into products. So as the reactants are converted to products, the reactants will get minus signs and the products will get plus signs. The value of that has to do with the given. Right now we don't know what that is, so let's call it X. That's what we call anything we don't know the value of. We do know that X is the same for each of these reactions. So now I have to ask myself, which is the limiting reactant? And we can do that by looking at the mole ratios and the givens. And I'm going to look at the mole ratios and say, well, I need 4 moles of aluminum for 3 moles of oxygen. I need more aluminum because for every 4 moles of aluminum, I'll react with 3 moles of oxygen. So 4 is greater than 3. I need more aluminum. Let's look down at the given. Do I have more aluminum? The answer is no. I do not have more aluminum. Therefore, I know that aluminum is the limiting reactant. And we can use this to solve for X. So my problem becomes 3.706 minus 4x equals 0. I got that from this column. So I'm going to use my regular algebra and solve for x. Add 4x to each side. Now I'm going to divide each side by 4 to cancel the 4 away from the x. And I get a value of 4x of 0.9265. And that's moles. So I can now go up here if I want and replace the value of x with the actual number. Now I can calculate. This column here for our product, which is the first thing it asks us for, is 0 plus 2x. I'll write it over to the side. So the last column, 0 plus 2x, is equal to 1.853. That's how many moles of aluminum oxide are produced. Now, how many moles of oxygen are left over comes from this column here. And that's 4.6875 minus 3 times 0.9265 equals. That's going to tell us how much oxygen, how many moles of oxygen are left over after the reaction stops. And that gives us 1.908. So how much oxygen is left over? 1.908 moles. So let's talk about what happened here. I put 100 grams of aluminum and 150 grams of oxygen in a reaction vessel. Once the reaction starts, I'm going to start producing aluminum oxide. So therefore, the amount of oxygen in aluminum is going to go down, and the amount of aluminum oxide is going to keep increasing until we run out of aluminum. When we run out of aluminum, the reaction stops, and no more aluminum oxide can be produced. All the aluminum's gone. The limiting reactant always ends up with 0. And then the reactant in excess is the one that we're going to have left over. How much do we have left over? Has to do with those mole ratios. So now if the problem asked us how many grams, I can go back up to here and say, in order to change moles to grams, I'll multiply by the molar mass. So I take 1.908, multiply it by 32, and I get an answer of 4 sig figs, 61.06 grams of O2 is left over. And then I'm going to take 1.853 and multiply it by the molar mass of Al2O3. The molar mass of Al2O3 is by adding each of the individual masses together. To get 101.96 grams per mole. So I take 101.96 grams per mole, multiply it by moles. That way the moles cancel out. And I get an answer to 4 sig figs of 188.9 grams of aluminum oxide. That's how many grams of aluminum oxide was produced. There is our first practice problem in limiting reactants with BCA charts.